Okay, so let's continue to our series of presentations. Next speaker is Professor Diego Hidalgo Leiva from the University of Costa Rica, and he's going to talk about the strong motion monitoring in Costa Rica. And he's going to talk about his lab, the Earthquake Engineering Lab.
Thank you. Well, good afternoon, all of you. Thank you for coming to Costa Rica. Thank you to Sergio for the invitation, and all the U.S. professors for bringing to Costa Rica this activity. We are very happy and very glad to have you, all of you here. Well, yeah, my presentation is a little bit about the strong motion monitoring in Costa Rica. The Earthquake Engineering Lab, or LIS in Spanish, stands for Laboratorio de Ingeniería Sísmica, the same. It's a lab that's part of the Engineering Research Institute, sorry. The Engineering Research Institute is not part of the Civil Engineering School, it's part of the Faculty of Engineering. And the next week, I think we have a visit to the Institute, and you will see some of our labs. Well, I will talk about the big earthquakes in Costa Rica, something about instrumentation history in Costa Rica, the products we generate for all the earthquakes, and some research topics we are working on. So, this information is from the Seismological Network of Costa Rica, RSN, here of the University of Costa Rica as well. Costa Rica has a high rate of seismicity. This is a map just with all the earthquakes with magnitude above 5.5 in the period of 1975 to 2017. So you can see that Costa Rica is a small country, more or less is the size of Lake Michigan, for example. We have 4 interacting plates, Coco, Nazca, Caribbean, and we have some information about this boundary here, which we call the Panama microplate. So it's a very complex scenario, seismicity, seismotectonic configuration. And as you can see in the stars are damaging earthquakes in this period. So we have a lot of fun here with the earthquakes. Since we're independent from Spain, for example, in 1921, we have had 68 damaging earthquakes, with 15 with the magnitude above 7. That it's a very big earthquakes for the tectonic we had. So you can see we have approximately 1 earthquake with magnitude above 7 every 13 years. So for this small country, this is a lot of earthquakes. The last big earthquake was here in 2012 with magnitude 7.6. And after the Cartago earthquake in 1910 with the MS 6.4, we have around 700 victims just in this earthquake. But after that, we just have around 100 victims. So for this amount of big earthquakes, we actually have a low fatalities or a low death rate. So the largest earthquake we have registered in Costa Rica is this one, is the Samara 2012. This is a 7.6 magnitude moment. The maximum acceleration was around 1,580 centimeters square seconds, or it's around 1.6 G, okay? The maximum acceleration was here. You can see the red dot. It's a very, very small area of the country. And we have the lucky, let's say, we have a station, an instrument right there about just over the epicenter zone. So this is the reason why we register this acceleration. This is real near field earthquake. In San Jose, is this region around there. We have a lot of information, but the accelerations were between, I don't know, 0.20, 0.50 G. So it's a big earthquake for the city, but it's not this acceleration of here. The attenuation of the waves is quite big. We have a lot of attenuation between these 2 points. This is typical for a large earthquake of this kind. This is a subduction earthquake. And as you can see here, we have the time in seconds. The duration of the earthquake over the epicenter zone was around 45 seconds. And you can see like a bunch of waves here, another one here, and third one here. This is because when the fault was rupturing, the rupture was not in just one segment, just one zone. It's a sequential falling, so we have different configurations of waves here. You can see it here as well, first, second, and third. This is very common in subduction, big subduction earthquakes as well. Well, the first accelegraph, the first equipment we received here in Costa Rica was in 1983 as a donation from the USAID program. First, this SMA kinematric equipment was received in the geology school, but this is a strong motion, so geology it's more related with not the strong motions, it's, the seismometers, not accelerometers. So they move all this equipment to the engineering faculty. This is our very first register here. This is from the earthquake in 1983 with epicenter in the south of the country, in Golfito. That was a 7.4 magnitude. And in San Jose, this was one of these SMA equipment, it had an acceleration of 41 centimeters square seconds. This is like 0.05 G around, more or less, yeah, or 5% of G. So this is our first record. This is an analogical record, and we had to digitalize after that. So we lost a lot of quality in this kind of records. Now we have a network with all the digital instruments. From 2006 until this year, well, 2018 actually, LIS receives funds from the National Emergency Law in order to purchase equipment, which allow us to improve the coverage. So you can see this is the coverage of the network up today, and we have more or less 120 instruments that are currently installed. We have instruments from multiple suppliers like Kinemetrics, Nanometrics, Goodalp, and Reftec. All these equipments are connected via internet, and we receive all this data in real time to our data center here in the University of Costa Rica. We have a lot of information that happens in real time, and I have a link here. Let's see if it works. It looks like they don't work. Let me see. I don't have internet. Okay. Nope, no internet. Good. Well, I will add the link there. If you want, you can go there later. So we receive all this information in real time to our data center. We process the information, and when an earthquake occurs, we display a lot of information about the earthquake. But information with engineering point of view. We don't like the magnitude, or we don't are interested in the depth or, I don't know, more seismological parameters. We're more interested in the PGA or in the response spectrum or some other intensity measures. So we display a lot of information after every earthquake. So you can go there and see, sorry, but we don't have internet right now. So part of our products, this is the last one maybe, it's very interesting. We are working on the early warning system. We call it the mass list. Mass is for the a secondary acceleration metrics. And you can go there. It's a tool that it's close to be early warning. We don't like to use actually the early warning word because it's very, let's see, tricky for the people to say we can tell you if you are going to fail or not the earthquake because we are surrounded of potential earthquakes. So if an earthquake occurs in the south or in the north of the country, yes, we have plenty of time here in the center of the valley of the center of the country. But if an earthquake occurs near us, we don't have time. So the early warning word it's tricky. So we are close to. So every 5 seconds, a series of parameters are calculated. We use the JMA intensity. This is the Japanese intensity scale as a trigger because we used to use the Mercalli intensity, but it's not quite accurate for damage or perception, so we use the JMA. It is a semi-real-time strong motion system, so you can go, I have a video, but we don't have internet, so I think it will not work. Let's check if we have internet now. No, I think we still don't have. Well, this video, if you go there later, you will see the system working in a real earthquake. So you will see here the JMA intensity measure, and right there in the right hand you will see the acceleration, the PGA. In this table we show the first 10 stations or first 10 points of the country with the highest acceleration. We have the traces here, the history, and the JMA quantification of stations per level. The JMA scale have 8 different scales or steps. So we have here all the stations in each one of these steps or scales. So I'm very sorry, but you will have to believe me that this works. We have also maps for activation of our major emergency protocols. I show you here 3 of our partnerships. We have one partnership with LanammeUCR, with the bridge section. I think Rolando talked a little bit, or Sergio, I'm not sure. After every earthquake with, let's see, with the magnitude intensity that triggered the system, we measure actually the risk in all these bridges. This is a semi-real time. We have this information about 15 minutes after the earthquake. So it's a semi-real time. It's not actually real time because we have to make a lot of calculations behind the scene. But we are able to display this kind of maps in order to activate some protocols of inspection or damage, revision, I don't know, or calculations. This one is with the Firefighters Department of Costa Rica, the institution. We have some equipment installed in the facilities of the firefighters. So after every earthquake, we plot here the JMA intensity for these facilities. So we can correlate the JMA scale with damage. This in the right hand, the last one, is with the Social Security, the health company in Costa Rica. We don't have this kind with so many stations, but each one of these points, it's one facility of the health security. And we extrapolate the data we have, and so we are able to present the GMA factor intensity. So we are making this kind of maps, but we are looking forward to present more technical information in all these facilities. We like to improve these kind of calculations with fragility curves or damage index or something more reliable. Our automatic reports, also we have, as I told you, after each earthquake, we have the automatic report. We have here, for example, the GMA for districts. So each one of these pieces of Costa Rica are one district. It's a political division from Costa Rica. So we were able to do this kind of extrapolation with data. We present for each station also the responding spectrum, and we compare this with the seismic code provisions. And we also have a lot of extra parameters. For example, the maximum response spectrum independent of the orientation, or what the ASCE calls the ROT D100 parameter. We calculate it in other way, but we have this presentation for each station, for each earthquake. Basically here you can see how the orientation, this is a 360 degrees plot, and this is the scale. This color is with a period. In blue we have very short period structures. In red, very long period structures. And the maximum response occurs between 0.2 and 0.5 seconds. This is the maximum amplification factor of a single degree of freedom. This is quite normal. But you can see the direction of the maximum amplification, the maximum response of the earthquake. So this is very, very interesting. We're working on that topic as well. The main research topics, internet, yeah, well, if you want. Si quiere revisar el problema de conexión. The main research topics of interest in LIS are the monitoring of strong motion. We have a lot of equipment installed in Costa Rica, so we record all the information, we process all the information, and we are helping, for example, in the hazard. Yeah. In the probabilistic hazard analysis of the Costa Rican, for Costa Rica, sorry. And actually we have a project related with LANAME and the seismology part of the university, and we are, in the next 3 years, we are aiming to improve the hazard analysis for Costa Rica. We need the records because we need the strong motion in order to measure the response, the amplification, and all the attenuation law or ground motion prediction equations. We are working on that. Let me show you, and we'll go back. Just I want to show you this video. Let's see. Yeah, bingo. So this is the, oh, okay. I have to close this. I'm not sure if the quality of the image, yeah, it's not quite good, but here is Costa Rica. All these dots are our stations. So you will see how this is the first station with a JMA factor above 4. And in seconds, all these stations here in San Jose. We felt in San Jose the earthquake. Here you can see the traces of the earthquake. I will stop right there. This is the first 2 stations, Puerto Jimenez and Ciudad Neyli. This is in the south. And in these 2 points, the earthquake, it's already paused, it's gone. And this one is here in La Sabana, in the main park of San Jose. Here, it's just arriving the S and P waves. So this time difference is because the distance between the focus of the earthquake and San Jose. We have a model. This is a very simplified model of the traveling time of the waves, but this is in real time. So we can go, this is just how the earthquake is finishing. All the lights means some level of the JMA scale. So here in San Jose was between 2 and 3. This is very low intensity for us. Intensity measures actually are related with the place you are measuring, because, for example, in a non-seismic zone, intensity of 4 could be huge. For us, an intensity 4, it's like every day. So we need like an intensity of 5 plus or something like that to really worry about. So yes, we have all the colors, and the earthquake now it's gone. So this is on real time, and we can go actually to the web page. Let me just a second. Okay, if you go to your cell phone or your device and go to Maslis, this is the web page. If you have better internet connection, you will see it fast enough. Yeah, it's working, believe me. And we have connected this system with Twitter, Facebook, Instagram, and all the social media networks. And after, I will go to Twitter. When the system just triggered the minimum intensity in 3 stations, we sent to Twitter these kind of pictures. We actually sent 5 pictures, one every 5 seconds. And you can see the evolution of the earthquake. This is in January 31. This was the last big earthquake, or at least felt in the country. So this is the first one, the first image. You can see this plot in red dots. It's an estimation of the epicenter. Localization of the epicenter is very rough, very unreliable, because we have just a few stations recording the earthquake. And we progress. We can see how San Jose, now it's in green. And this is the last one. And we have a better approximation of the epicenter. We have another system working in parallel to define of this parameter. This is a very quick, very immediate tool. So it's almost real time, but it's not actually real time. We have like a delay of some seconds, but we are testing the system with different kind of tools, for example, with SMS cell phone, or WhatsApp or Telegram, in order to send to the people the alert. We're working on the application as well, and we will have all this information, quicker. So yes, the main research topics, I told you: the monitoring of strong motion, the seismic risk reduction and mitigation, soil effects due to the earthquake and their interaction with the structures, structural dynamics, structural health monitoring, and some other topics I don't mention here. I just want to show you some 2 projects besides the strong motion monitoring. We are working on a seismic risk assessment in San Jose Canton. This is a project we have with the German Research Center of Geoscience in Potsdam in order to improve the exposure model, because we have many studies in hazard, but we don't have studies in exposure. And exposure is very needy, because when you want to measure the risk, you have to combine the exposure, the vulnerability, and the hazard. And this exposure model is actually quite necessary. We took photos like the Google Street View, because we don't have it here in Costa Rica, so we managed to bring this camera from Germany, and We took a lot of pictures, actually around 34,000 pictures. Every one of these points is a picture. We defined this route. This is the Canton of San Jose. We are not here. We are outside San Jose Canton. But this is the main commercial and urban area of San Jose. This is the footprint of the city. You can see an example here. We have in total around 80,000 structures exposed here. This is a lot of structures. And this is an example of the RRVS, the Rapid Visual, let me see how we define this, the Remote Rapid Visual Screening. So we have in the left hand the 360 degrees photos. We have in the right hand the satellite pictures. And we evaluate each one of the structures selected in a probabilistic way in order to complete the task. From these near 80,000 structures, we are evaluating just around 8,000. But 8,000 structures is a lot of work. We are working since 1.5 years now, and we will finish this, I hope, this year. Second, I want to show you this project, this capacity and nonlinear characterization of reinforced concrete masonry. We are working as well with the LanammeUCR in the material and structural models. And this project have the natural scale test of masonry walls with the typical typology of construction typology of masonry in Costa Rica. It's a mixture between the reinforced masonry and confined masonry. This is a photo of the walls. Actually, Monday, I think we will visit the LanammeUCR and you will see these walls there. Our construction method is with the masonry, reinforced masonry, but we put a frame, a reinforced concrete frame around the masonry wall. And this is a more complex system because we have the interaction between the frame, the concrete frame, and the reinforced masonry. So it's an interaction between a lot of materials, different materials. We have partially grouted masonry. It's not fully grouted. We just put grout concrete in the vertical reinforce. And we have also horizontal reinforce between, I think, every 2 or 3 cells, I'm not sure. This is our main wall, the reaction wall and the reaction floor. And this wall, it's 3 meters tall. This is like 10 foot, I think, yes. And around 6 meters long. This is HL leg height relationship of 2 or 0.5, depends on how you put the parameters. And we come from 2, or the larger this one, to this more slender wall. We are trying to characterize the rigidity degradation related with the slenderness. Well, yeah, finally, we have right now 9 buildings with at least 1 accelegraph on the basement or in free field, and 1 on top floors. You can go to our webpage. We have collaboration agreements with public and private clients. We have 1 borehole installed, and 1 more will be installed this month. So we have a lot of information coming from a lot of different structures. So this is the presentation I bring to you today. Thank you for being here in Costa Rica. My intention with this presentation is to show you all the possibilities we have to work together and try to make something. We have a lot of information, a lot of energy. We don't have enough people, but we're trying to make a research group here in Costa Rica with Sergio, LanammeUCR, and all the other engineers around us. Thank you.